Have you ever wondered what truly keeps our lives so peaceful? Sometimes the answer doesn't lie in the grand things, but in the small, silent pieces that move quietly around us. Now, look up at the solar system. Instead of the brilliant, massive planets, tonight's sleepy universe invites you to visit humbler worlds. The moons. They are our strange, surprising neighbors. Worlds that are often overlooked on star charts. Let your mind drift as we begin a journey to discover these forgotten beauties right in our own celestial backyard. Because the smallest worlds, at times, tell the greatest stories of all. Phobos is the larger of Mars's two moons, and the more unsettling one. At first glance, it barely looks like a moon at all. It's small, misshapen, dark, more like a captured asteroid than a world that formed neatly beside a planet. Its longest dimension is only about 27 kilometers, smaller than many major cities on Earth, and nowhere near the scale of anything we'd normally call planet-like. But the strangest thing about Phobos isn't its shape. It's where it lives. Phobos orbits Mars so low that in cosmic terms, it's skimming the surface. It circles the planet in a little over 7.5 hours, faster than Mars can rotate beneath it. That means if you were standing on Mars and you could see it through the thin sky, Phobos would rise in the west and set in the east, moving unusually fast, like something that doesn't quite belong. And it's not just passing by. Phobos is slowly losing altitude, not dramatically, not in a way you could notice in a lifetime, but measurably. Year after year, it spirals inward by a tiny amount, pulled by the tidal forces of the planet it orbits. The same gravity that keeps it from drifting away is also the gravity that's quietly tightening the leash. This is what makes Phobos feel different from most moons we talk about. Most moons feel stable, permanent. Phobos doesn't. It's a moon on a countdown. If the slow inward drift continues, Phobos has two possible endings, both inevitable, just with different timing. One outcome is a collision. The moon eventually falls into Mars and becomes part of the planet's surface. The other outcome happens sooner. As it gets too close, tidal forces can begin to overwhelm its weak internal strength, cracking it apart and stretching it into a ring, a temporary band of debris around Mars, lasting for a while before it rains down, and we may already be seeing the early signs. Phobos is carved with long, straight grooves, shallow, parallel lines that run across its surface like scars. For a long time, people debated what made them. One idea was impact ejecta, debris blasted out from a giant crater, like Stickney, that raked across the surface. But another explanation has grown more compelling. Stress fractures. The moon flexing under tidal strain, cracking as it's pulled and squeezed, again and again. Phobos has no atmosphere, no weather, no geology actively rebuilding the surface. So once a crack forms, it stays. That's the quiet discomfort of Phobos. Not because it's dangerous to us, but because it shows something we don't like to admit about small worlds. Orbits can decay, and even moons can have a lifespan. And if Phobos is a moon in slow collapse, its smaller companion tells a very different story. If Phobos feels like a moon in trouble, Deimos feels like a moon that learned how to stay out of it. Deimos is the smaller of Mars's two moons. Its longest dimension is only about 15 kilometers, and it orbits much farther out at an average distance of roughly 23,500 kilometers from the surface of Mars. That distance makes all the difference. While Phobos skims dangerously close to the planet, Deimos keeps a safer orbit. Mars's tidal forces still reach it, but only weakly. The constant squeezing and flexing that slowly tears Phobos apart barely affects Deimos at all, and the surface reflects that. Deimos looks calmer. There are fewer long grooves, fewer signs of structural stress. Its shape is still irregular, more like a lumpy rock than a rounded world. But it doesn't look strained. It doesn't look like it's being pulled in too many directions at once. In orbital terms, Deimos lives in a quiet neighborhood. That quiet is what makes it strange. Despite being smaller and farther away, Deimos is harder to explain than Phobos. Its origin is still debated. One possibility is capture. That Deimos began as a small asteroid wandering through the inner solar system before Mars's gravity claimed it. Another idea suggests it formed closer to Mars, from debris already bound to the planet, gradually coming together rather than being violently grabbed. The problem is that Deimos doesn't clearly support either story. Its orbit is orderly. Its surface doesn't preserve obvious clues. And unlike Phobos, it isn't changing fast enough to force answers. Nothing appears to be breaking. Nothing is obviously out of place. And because of that, Deimos has been studied far less. There's no countdown here. No visible collapse. No dramatic future scenario to model. Deimos doesn't demand attention, and so it often doesn't get it. But that absence is information. Deimos shows us what happens when a small moon escapes strong tidal stress. It shows what long-term stability looks like in a system where gravity usually creates tension. No internal heating, no resurfacing, no visible decay, just persistence, stretching quietly across billions of years. We tend to associate weird with activity, with eruptions, fractures, motion. Deimos suggests something subtler, that stability itself can be strange, that a world can remain largely unchanged for immense spans of time and still matter deeply to how we understand planetary systems. Phobos shows us that orbits can decay. Deimos shows us that some orbits simply endure. But Mars is only the beginning. To find truly extreme moons, we have to leave the inner solar system. By the time you reach Callisto, the mood of the story changes. With Phobos and Deimos, we were talking about small moons close to home, fragile worlds shaped by proximity, by stress, by the slow math of gravity. Callisto is different. It's not close. It's not fragile in the same way. And it doesn't feel like a world that's still being rewritten. Callisto is the outermost of Jupiter's 4 Galilean moons, the one that keeps its distance. It's about 4,820 kilometers across, nearly the size of Mercury. And yet, it carries none of the youthful drama you might expect from a body that large. It doesn't erupt like Io. It doesn't flaunt a smooth, freshly cracked ice shell like Europa. It doesn't advertise a magnetic surprise the way Ganymede does. Instead, Callisto preserves. When you look at its surface, what you're really seeing is time. Stacked in layers, left exposed. Callisto is covered in impact craters. Not just a lot of craters, but so many that it's close to saturation. Meaning, new craters have nowhere clean to land without overlapping old ones. If you want an image of a world that has spent billions of years simply taking hits and keeping the evidence, Callisto is that image. And that's the key idea here. On Earth, most scars don't last. Weather erases them, water reshapes them, plants break down rock, volcanoes repave the land. Plate tectonics folds the crust and recycles it. Earth is one of the least cratered surfaces in the solar system, precisely because so much is always happening. On Callisto, almost nothing happens. Its tidal forces are weak. Its internal activity is minimal. There's no global resurfacing to wipe the slate clean, so the surface remains intact. And that makes it a kind of fossil, a preserved record from the early solar system. That record includes some truly enormous structures. One of the most impressive is Asgard, the second largest impact basin on Callisto, measuring about 1,600 kilometers across. And then there's Valhalla, the largest multi-ring impact crater in the entire solar system, spanning roughly 3,800 kilometers in diameter. These aren't just craters. They're continent-scale wounds, surrounded by multiple rings like ripples frozen into rock and ice. Crucially, impacts like these may have done more than scar the surface. They may have punctured Callisto's crust. And then, over time, that crust refroze and sealed itself again, leaving behind the lighter patches you can see in the interior regions. It's one of the strangest things about Callisto. It wears its violence openly, but it also looks settled. Like the violence happened long ago, and the moon simply accepted it. Zoom in closer, and the surface gets even stranger. In some regions, you can see a mottled, mixed appearance. Bright knobs scattered over darker plains. Those knobs are thought to be the degraded remains of countless ancient crater rims, softened and worn down over time. Not by wind, not by rain, but by slow processes in ice and rock that work over geological timescales, even when nothing active is happening. And in a subtle way, Callisto's craters are unusual. Many impact craters here are shallower than you'd expect. For example, there's an impact structure over 100 kilometers wide that's only about 600 meters deep. That kind of shallowness hints at something beneath the surface, something that can relax, slump, or flow very slowly, reducing a crater's depth over time. Which brings us to the strange possibility Callisto refuses to announce out loud. Despite looking like a dead world, Callisto may not be entirely solid inside. Measurements suggest its crust could be on the order of 80 to 150 kilometers thick. And beneath that, there may be soft ice or even a salty subsurface ocean. The evidence is indirect. Data consistent with a conductive layer, something that can respond to Jupiter's powerful magnetic environment. And there are hints of a small rocky or silica-rich core at the center. But if that ocean exists, it would be a quiet one. Callisto is far from the strongest tidal heating in Jupiter's system. It receives very little warmth from the sun, and it doesn't get needed the way Europa does. That means the main heat sources would be limited, mostly slow radioactive decay inside the moon. And because of that, most scientists think the conditions needed for life are less favorable here than on other icy worlds. Low energy means fewer opportunities for chemistry to stay active over long periods. And yet, Callisto remains valuable. Because in human terms, it may be the safest place in Jupiter's neighborhood. Callisto orbits at about 1.9 million kilometers from Jupiter, beyond the planet's main radiation belts. Compared to Europa, that makes its environment thousands of times more hospitable for exploration. Not comfortable, not easy, but meaningfully safer. A world where you could imagine, one day, a base, a way station, a place to live far enough from the worst of Jupiter's radiation, while still close enough to explore the inner system. This is the twist of Callisto. Europa may be the moon with the bigger dream, a hidden ocean with the strongest promise. But Callisto might be where humans go first, simply because it's stable, because it's quiet, because it doesn't punish you immediately for being there. Sometimes, stability is what matters most. Callisto shows us endurance on a grander scale, a world that has spent billions of years not changing much at all, and is valuable precisely because of that. And that's where the story turns again. Because the next moons don't just preserve the past, they rewrite it. But some moons don't just preserve the past, they actively reshape themselves. If Callisto is the moon that preserves history, Ganymede is the moon that hides a whole planet's worth of physics beneath the ice. Ganymede is the largest moon in the solar system. Its diameter is about 5,268 kilometers, roughly 0.41 Earth's diameter. And by volume, it's enormous, about 26% larger than Mercury. It doesn't have Mercury's mass because it isn't made mostly of dense metal. But in sheer size, it's hard to call it just a moon. In fact, for a long time, Titan was thought to be the biggest. Titan looked bigger because its thick atmosphere extends hundreds of kilometers into space. But once you measure the solid body itself, Ganymede takes the title. And it isn't close. Ganymede is rich in water ice. Like Europa, its surface is a thick crust of ice. And beneath it is the real reason scientists can't stop thinking about this world: a hidden ocean. The estimates are staggering. That ocean may contain more water than all the oceans and seas on Earth combined. And it's thought to be immense. On the order of 100 kilometers deep on average, about 10 times deeper than the deepest point in Earth's oceans. Put simply, Ganymede is not a rock with a little ice on top. It's closer to half rock, half water, with small amounts of metals and other ices mixed in. Its average density reflects that, around 1.9 grams per cubic centimeter. Far less than Mercury's 5.4, because water drags the average down. And then there's the atmosphere. Ganymede has oxygen in its tenuous atmosphere. That sounds dramatic until you look at the numbers. The pressure is estimated to be somewhere around 0.2 to 1.2 micropascals. That's roughly 100 to 500 billion times less than Earth's atmospheric pressure at sea level. It's not something you could breathe. It's not even close. But it's still a clue that chemistry is happening at the surface, driven by radiation and energetic particles. At this point, it's tempting to ask the obvious question. With water and oxygen, could there be life? It's not impossible. Earth has already proven that ecosystems can thrive in dark oceans without sunlight, powered by chemistry instead of photosynthesis. But Ganymede has a serious obstacle. Its ocean may be so deep that the water near the bottom gets squeezed into exotic high-pressure forms of ice. If that happens, it creates a barrier. Thick, solid ice separating the liquid ocean above from the rocky core below. And without contact between water and rock, you lose one of the most reliable engines for ocean chemistry: minerals and heat from the interior. Europa is often considered the stronger candidate for life, partly because its ocean is more likely to interact with rock. But here's where Ganymede becomes complicated. There's growing evidence that the ocean is salty, and that matters. In some models, a salty ocean changes how Ganymede's interior layers stack up. Instead of one simple ocean sitting on rock, there may be multiple liquid layers separated by sheets of ice. And it's possible that the deepest liquid layer could still touch the rocky interior. That would raise the odds that chemistry, and maybe biology, could find a foothold somewhere down there. So Ganymede is already strange. A moon bigger than Mercury by volume, a water reservoir larger than Earth's oceans, an oxygen atmosphere that's real but nearly non-existent. And then it does something no other moon does. It produces a magnetic field. This is the part that breaks intuition. Ganymede's magnetic field was discovered during flybys by the Galileo spacecraft in the 1990s. One of the clearest signatures of a magnetic field is auroras. And auroras were detected in Ganymede's thin atmosphere. Later, long observations by Hubble showed something else. Those auroras didn't wobble as much as expected. One possible explanation involves a salty ocean beneath the surface, creating a kind of magnetic friction, a response that subtly changes how the auroras move. A magnetic field is a big deal because it's the feature that helps shield Earth from solar radiation. It's part of what makes our surface environment stable enough for life to flourish. Ganymede's field doesn't fully protect it. Not inside Jupiter's system. Jupiter's magnetic environment is brutal. Even on Ganymede, the surface can still receive something like 5 to 8 rem, enough to make a human severely ill, or worse, in as little as a couple of months. But compared to moons closer in, it's still an improvement. And more importantly, it means Ganymede behaves like a world with a deep, active interior. The mystery is, why? On Earth, our magnetic field comes from a hot, liquid, convecting core, moving electrons, generating a dynamo. But Ganymede is smaller than Earth. Based on its size and composition, many scientists would expect its core to have cooled enough by now to become mostly solid. And if the core is solid, you shouldn't get the kind of convection that powers a global magnetic field. Yet the field is there. And Ganymede is the only moon in the entire solar system known to have one. So the best explanations point back to motion and stress. Ganymede orbits Jupiter about once every 7 days. But its path isn't a perfect circle. As it moves along that slightly uneven orbit, Jupiter's gravity doesn't pull on it the same way all the time. Sometimes the pull is stronger. Sometimes it eases. And over millions of years, that constant tightening and releasing gently warms the moon from the inside. The way bending a paperclip over and over slowly heats the metal. And Ganymede doesn't do this alone. It's locked into a resonance with Io and Europa, a precise gravitational rhythm. For every 1 orbit Ganymede completes, Europa completes 2, and Io completes 4. A 4 to 2 to 1 resonance that helps maintain orbital eccentricity and keeps tidal forces from fading away. Ganymede is, in a sense, a moon shaped by relationships. It's a water world, a layered world, a world with auroras, a world with a magnetic mystery. Ganymede's magnetic field tells us something is moving deep inside the moon. But it doesn't tell us how close that hidden ocean is to rock, or whether chemistry there can stay alive. For that, we have to look at a moon where the ice is thinner and the energy runs hotter. Before we continue, thank you for being here. If this video helps you relax or learn something new, a gentle like really helps the channel. And if you'd like more calm journeys like this, you're always welcome to subscribe. Now, let's continue. Europa is smaller than Ganymede. Its diameter is about 3,120 kilometers, making it roughly the size of Earth's moon. And yet, in many ways, Europa carries a heavier scientific weight than any other moon in the solar system, because Europa looks alive, even though almost everything about its surface should be deadly. At first glance, Europa is strikingly bright. Its surface is covered in ice, reflecting sunlight far more efficiently than most worlds at Jupiter's distance. And unlike Callisto, Europa has very few impact craters. That absence is important. Craters accumulate when a surface stays the same for long periods of time. Europa's smoothness tells us that something is constantly renewing it. The ice doesn't sit still. Stretching across Europa's surface is a vast network of dark lines, fractures and ridges that run for hundreds, sometimes thousands of kilometers. They crisscross the moon like stress marks in glass. In some regions, the ice looks broken, rotated, and reassembled into jumbled blocks. Scientists call these areas chaos terrain. The name sounds dramatic, but the implication is even more so. Chaos terrain suggests that the ice shell has partially melted, shifted, and refrozen. Not once, but repeatedly. Which means Europa isn't just frozen solid, it's being warmed from below. That warmth does not come from the sun. Europa orbits deep inside Jupiter's gravitational grip. Like Ganymede, its orbit is slightly eccentric, and it's locked into a resonance with neighboring moons. As Europa moves closer to Jupiter and then slightly farther away along its orbit, the planet's gravity flexes the moon, stretching it, compressing it, and releasing it again. Over millions of years, that constant motion generates heat inside the moon. This process is known as tidal heating, and on Europa, it's strong enough to keep a global ocean from freezing solid. Beneath Europa's ice shell, which may be anywhere from 15 to 25 kilometers thick, lies a vast ocean of liquid water. Estimates suggest this ocean could be over 100 kilometers deep, containing more water than all of Earth's oceans combined. A global ocean, in permanent darkness, sealed beneath ice. That alone would be remarkable. But Europa's environment is far more complicated and far more dangerous than that. Europa sits deep within Jupiter's radiation belts. Charged particles are constantly accelerated and slammed into the moon's surface. The radiation levels are extreme. A human standing unprotected on Europa's surface would receive a lethal dose in minutes to hours, depending on location. No atmosphere, no magnetic shield strong enough to help. Europa's surface is one of the most hostile places a human could ever visit. And yet, that same radiation does something unexpected. When high-energy particles strike Europa's ice, they break apart water molecules. This process, called radiolysis, produces molecular oxygen and other oxidants. Some of that oxygen escapes into Europa's incredibly thin exosphere. It's not breathable. The pressure is effectively zero. But chemically, it matters. Because oxidants are energy-rich molecules, if even a small fraction of that oxygen is transported downward through cracks, melt-through events, or slow mixing, it could reach the ocean below. And if it does, it could provide a powerful chemical energy source. This is where Europa becomes more than just an ocean world. Life, as we know it, doesn't require sunlight. On Earth, entire ecosystems thrive around hydrothermal vents, powered by chemical reactions instead of photosynthesis. What they need is liquid water, energy, and chemistry that stays out of equilibrium. Europa may have all three. Evidence for the ocean doesn't come from a single measurement. It comes from patterns. As Europa moves through Jupiter's magnetic field, it generates a secondary magnetic signal, one consistent with a conductive layer beneath the surface. Salt water conducts electricity. Pure ice does not. The simplest explanation is a salty global ocean responding to Jupiter's magnetic environment. There have also been tantalizing hints of something even more direct. On several occasions, telescopes have observed possible plumes of water vapor rising above Europa's surface. Similar to the geysers on Enceladus, though much less certain. These observations are difficult, they're intermittent, and they haven't been confirmed beyond doubt. But even the possibility matters. Because if water is occasionally reaching the surface, or space, then Europa's ocean may not be completely sealed off. It may be exchanging material with the surface above, and that exchange is exactly what astrobiologists look for. Europa doesn't make this easy. Its ice is thick, its radiation environment is brutal. Landing there would be extraordinarily difficult. Drilling through kilometers of ice would be a technological challenge far beyond anything we've done before. And yet, Europa remains one of the highest priority targets in planetary science. Not because we expect to find life tomorrow, but because Europa represents a test of the idea that life doesn't need Earth-like conditions, that oceans can exist in darkness, that ice can be protection, not a barrier. Europa is a moon where the surface tries to kill everything, while the interior may quietly support the conditions needed for life. That tension is what makes it extraordinary. Hope wrapped in danger. Possibility sealed beneath ice. Europa doesn't shout its secrets. It hides them. But if Europa hides its energy beneath the ice, another moon releases it violently. If Europa hides its energy beneath layers of ice, Io does the opposite. Io releases everything. Io orbits extremely close to Jupiter, at an average distance of about 421,700 kilometers, closer than any other large moon in the system. At that range, Jupiter's gravity doesn't just hold Io in place, it works it constantly, relentlessly. And Io isn't alone. Its orbit is locked in a precise gravitational rhythm with Europa and Ganymede. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. A 4-to-2-to-1 orbital resonance. That arrangement keeps Io's orbit slightly stretched instead of circular. And that tiny stretch is everything. As Io moves closer to Jupiter, it's pulled harder. As it moves slightly farther away, the pull eases over and over again. As Io moves along its orbit, Jupiter's gravity never pulls on it evenly. The force rises, then eases, then rises again and again, without rest. That repeated motion doesn't crack the surface right away. It builds heat deep inside. On Io, this flexing happens across the entire moon. The interior warms, pressure builds, and molten material is constantly pushed upward, looking for a way out. Rock doesn't need to melt completely to change. Under enough stress, it flows. The result is staggering. Io is the most volcanically active body in the entire solar system. More than 400 active volcanoes have been identified, and many of them erupt continuously. Some lava fountains shoot hundreds of kilometers into space. Some plumes rise so high that they briefly escape Io's gravity before falling back down like ash. And this isn't water-based volcanism. Io has no surface water, no ice shell, no oceans. Temperatures swing wildly, but the surface is dry, brittle, and saturated with sulfur and sulfur dioxide. The lava flows here are rich in sulfur compounds, creating colors that feel almost unreal. Yellows, reds, blacks, whites, repainting the surface again and again. Io doesn't age the way other worlds do. On most moons, impact craters accumulate over time. They pile up like scars. On Io, they don't last. The surface is resurfaced so frequently that craters are buried, flooded, or erased before they can tell a long story. In geological terms, Io's surface is extremely young, constantly reset by eruptions that never quite stop. If Callisto is a fossil, Io is the opposite. It's a world that refuses to settle. The energy involved is hard to overstate. Io produces more internal heat than Earth does, despite being far smaller. And that energy doesn't stay contained. As Io's volcanoes erupt, gases escape into space, forming a thin, constantly replenished atmosphere, mostly sulfur dioxide. From there, atoms are stripped away by Jupiter's intense magnetic field and become ionized. Those ions don't drift randomly. They form a plasma torus, a glowing ring of charged particles that wraps around Jupiter at Io's orbital distance. In a very real sense, Io feeds Jupiter's magnetosphere. The Moon loses material, and Jupiter gains it. There is even an electrical connection. As Io moves through Jupiter's magnetic field, it acts like a conductor cutting through invisible magnetic lines. This generates an electrical current, sometimes described as a flux tube, that links Io directly to Jupiter's atmosphere. Energy flows along this path, creating bright auroral footprints where the connection touches Jupiter's poles. Io is not just orbiting Jupiter, it's interacting with it, continuously. This is energy without moderation. On Europa, tidal heating is controlled enough to keep water liquid without destroying the structure above it. On Io, the same fundamental mechanism has gone too far. There is no buffer, no protective shell, no stable balance point. Everything that can melt, melts. Everything that can erupt, erupts. From a scientific perspective, Io is invaluable. It shows us what happens when tidal heating dominates a world completely. It provides a natural laboratory for understanding volcanism under extreme conditions, far beyond anything we can recreate on Earth. It reminds us that gravity alone can power geology, without sunlight, without radioactivity as the primary driver. But from a biological perspective, Io is a dead end. There is energy here, enormous energy, but no place for it to settle into complexity, no liquid water to act as a medium, no stable chemical gradients that persist long enough to build anything delicate. Whatever chemistry starts is torn apart almost immediately by heat and motion. Energy is necessary for life, but energy alone is not enough. Without balance, energy becomes destructive. And that's what makes Io such a powerful counterpoint to Europa. Europa hides its heat beneath ice, protecting it. Io exposes its heat at the surface, unleashing it. Not all moons whisper their secrets. Some scream them into space. After the intensity of Io, Rhea asks us to slow down. Rhea is Saturn's second largest moon, about 1,528 kilometers across. Large enough to be geologically meaningful, but small enough to remain quiet. From a distance, it looks exactly like what you expect an icy moon to look like. Pale, cold, and heavily cratered. A surface shaped far more by time than by activity. And that first impression isn't misleading. Rhea shows little evidence of internal heating today. No active volcanism, no geysers, no resurfacing events that would erase its past. The craters remain, layered across the surface like a long record of impacts that were never wiped away. But Rhea isn't featureless. Running across parts of its surface are faint, bright markings, delicate, thread-like patterns, once referred to as wispy streaks. Early on, their origin wasn't clear. They didn't behave like cracks or tectonic lines. Over time, the explanation became more grounded. These streaks are likely ice cliffs, steep scarps where cleaner, brighter ice is exposed, reflecting more sunlight than the surrounding terrain. Subtle, local, and consistent with a moon that has changed very slowly. Rhea also has something even thinner than its surface features, an exosphere. Not a true atmosphere, but a sparse cloud of particles containing trace amounts of oxygen, O2, and carbon dioxide, CO2. These molecules are produced when radiation and sunlight interact with surface ice, knocking atoms loose over long periods of time. The quantities are tiny, but their presence tells us that chemistry doesn't stop just because a world is cold. For a while, though, Rhea seemed to promise something far more dramatic. Data hinted at the possibility that Rhea might be surrounded by rings, faint bands of material orbiting the moon itself. If true, it would have been extraordinary. Rings are usually associated with planets, not moons. A moon with its own ring system would have forced scientists to rethink how small bodies interact with debris in orbit. It was an exciting idea, but excitement isn't evidence. Cassini, the spacecraft orbiting Saturn, had a rare advantage. It could fly directly through the region where the ring material was supposed to exist. If there were particles there, dust, ice grains, anything substantial, Cassini's instruments should detect them. So Cassini crossed the region, and it didn't find them. No dust impacts, no particle density changes, no material consistent with a ring system. The hypothesis didn't survive the test. And that outcome mattered, not because something spectacular was discovered, but because something wasn't. The absence of ring material wasn't a failure of observation. It was a clean result, a clear answer to a specific question. Rhea didn't reveal a hidden structure. It revealed a limit. And that's the role it plays in this story. Rhea represents a kind of scientific honesty that often gets overlooked. Not every mission uncovers a breakthrough. Not every anomaly becomes a discovery. In that sense, Rhea is not disappointing. It's grounding. It gives us confidence in the method that lets us chase the next one. And that quiet clarity is exactly what prepares us for what comes next. Titan is the kind of world that can trick your instincts. From far away, it looks quiet. Just another distant moon orbiting Saturn, far from the sun's warmth. But as soon as you get closer, Titan stops feeling like a moon and starts feeling like a place. A place with air, with weather, with a horizon that could almost belong on Earth. Titan is Saturn's largest moon. Its diameter is about 5,150 kilometers, larger than the planet Mercury. And unlike most moons, Titan is wrapped in a thick atmosphere. Mostly nitrogen, like Earth's, but laced with methane and a haze of complex organic aerosols that tint the sky a deep orange. That haze changes everything. Sunlight at Saturn is already weak, about 1% of what we receive on Earth. And Titan's atmosphere filters it even further. The light is dim and diffuse, as if you're watching the world through tinted glass. Nothing is sharp. Shadows soften. The landscape looks muted and dreamlike, even when the physics behind it is anything but. For a long time, Titan was a mystery because the haze hid the surface. We could measure its size and mass. We could detect the atmosphere. But the ground itself was invisible. Then, in 2005, something extraordinary happened. The Huygens probe separated from the Cassini spacecraft and descended through Titan's atmosphere, falling for more than 2 hours before touching down. It didn't land on liquid. It didn't sink into dust. It landed on solid ground and sent back images of a landscape that looked uncomfortably familiar. Rounded pebbles, channels, a surface shaped by flow, not by lava, not by ice cracking, by something that behaves like rain. Titan has wind. Titan has weather. Titan has storms. It has erosion. It has rivers that carve channels and carry material downslope. It has plains and basins and lowlands that collect liquid. And this is where the twist begins. Because Titan has all of those Earth-like behaviors without the one thing you would expect them to require: water. Titan is cold, around 94 Kelvin, about -179 degrees Celsius. At that temperature, water is rock hard. It doesn't act like a fluid. It doesn't run. It doesn't evaporate and fall as rain. On Titan, water behaves like granite. So what's flowing? Methane and ethane. On Titan, methane takes the role that water plays on Earth. It moves through the environment in a slow, familiar rhythm, rising into the atmosphere, forming clouds, falling back as rain, and carving paths across the surface before settling into lowlands and seas. Titan runs a methane cycle the way Earth runs a water cycle. In the warmer moments of Titan's seasonal rhythm, methane evaporates from the surface and from polar seas. It rises, cools, and condenses into clouds. Those clouds thicken, drift, and sometimes release rain. Not gently, but in sudden downpours strong enough to reshape the ground. The liquid then runs downhill through channels and rivers, pooling in basins, soaking into porous materials, or collecting again in lakes and seas. Weather. On a moon, Titan even has something like climate. Saturn takes nearly 29.5 Earth years to orbit the Sun, and Titan's seasons follow that slow clock. The changes aren't fast. They're patient, but they're real. Over years, methane migrates, lakes grow or shrink, clouds shift, and the surface responds. And because Titan is active, then it doesn't keep scars the way Callisto does. Its surface is relatively young. It has fewer large impact craters than you'd expect for a world of its age, which tells us that something, rainfall, sediment transport, possible cryovolcanism, and atmospheric chemistry, has been slowly refreshing the landscape. So Titan becomes a paradox. It feels right, because it has air, wind, rain, rivers, and a sky. But it's built from the wrong materials. The rivers aren't water, the seas aren't water, the rain isn't water. Even the ground you stand on would be alien. If you could step onto Titan, the pressure at the surface would be about 1.5 times Earth's. The gravity would feel gentle, only about 14% of Earth's gravity. You could move easily. You could jump higher. You might even feel, for a moment, as if this world was welcoming, but it wouldn't be. The air would be cold enough to freeze exposed skin quickly. And the liquids flowing around you, methane and ethane, are not just unfamiliar. They're the kind of chemistry that reminds you this is not Earth with different scenery. It's a different kind of planet-like world entirely. And yet, Titan is not dead. It is chemically rich. Its atmosphere continuously produces complex organic molecules, the raw ingredients of prebiotic chemistry. The surface cycles liquids through an active system. The weather keeps shaping the land. It's a living process, even if it doesn't produce life as we know it. That's what makes Titan so captivating. It's a world that echoes Earth just enough to pull you in, and then quietly forces you to admit that your intuition is built for one planet only. Titan teaches a gentle but unsettling lesson. Familiarity can be a trap. A landscape can look recognizable while operating under completely different rules. And once you accept that, Titan becomes even more strange. Because the most Earth-like part of Titan isn't its sky. It's its seas. And if Titan feels alive, its lakes are where that lifelike behavior becomes impossible to ignore. If Titan feels alive, its lakes are where that feeling becomes quiet. Most of Titan's liquid doesn't spread evenly across the surface. Instead, it gathers near the poles, especially in the north, where temperatures are lower and methane can remain liquid for long periods of time. From orbit, these regions appear dark and smooth, scattered with shapes that resemble seas, bays, and winding shorelines. But these are not oceans of water. They are lakes and seas made of liquid methane and ethane, held in place by cold so intense that water behaves like stone. Some of these bodies are enormous. Kraken Mare, the largest, stretches for hundreds of kilometers, comparable in size to Earth's largest seas. Others are smaller, shallower, and scattered like pools across the polar terrain. For years, these lakes were hidden. Titan's thick atmosphere blocks visible light, making traditional imaging almost useless. To see the surface, the Cassini spacecraft relied on radar, sending radio waves through the haze and measuring what bounced back. When those signals returned unusually strong and clean, scientists realized they were seeing something special: flat surfaces. In some regions, the radar reflections behaved like a mirror, a phenomenon known as specular reflection. That kind of signal only comes from something extremely smooth. On Earth, it's what you see when radar hits calm water at just the right angle. And on Titan, it revealed something unexpected. The surfaces of these lakes were almost perfectly still. No whitecaps, no rolling swells, no constant motion. Compared to Earth's oceans, Titan's seas are unnervingly calm. This absence of waves isn't a coincidence. Several factors work together to suppress motion. Titan's winds are generally weak near the surface. The gravity is low, which changes how fluids respond to energy. The liquids themselves are different, with physical properties unlike water. And the cold makes everything move more slowly. Even when wind does pass over the lakes, it rarely transfers enough energy to raise visible waves. The result is a surface that stays flat for long stretches of time, broken only occasionally by subtle ripples during seasonal changes. In a strange way, Titan's lakes behave less like oceans and more like polished stone. But the stillness doesn't mean nothing is happening. Over time, Cassini noticed something odd in a few of these seas. Bright features would appear, then fade, then reappear somewhere else. They were nicknamed magic islands, not because they were mysterious objects, but because they refused to behave consistently. These features changed with viewing angle and time. Sometimes they looked solid. Other times, they vanished completely. Several explanations are still being explored. Floating chunks of hydrocarbon ice, bubbles rising from below, shifting surface roughness, or temporary changes in reflectivity caused by wind or temperature. None of these explanations are dramatic on their own, but together, they point to something important. Titan's lakes are not static. They respond to seasons. As Titan moves slowly around the sun, methane migrates. Some lakes grow, others shrink. Shorelines advance and retreat. Liquids are redistributed across the surface on timescales measured not in days, but in years. Titan runs a hydrological cycle, just not a fast one. This slowness changes how the world feels. On Earth, water is restless. Waves never stop. Motion is constant. On Titan, liquid can remain still long enough to feel permanent. The environment encourages patience. Processes unfold gradually, almost quietly, as if the moon is in no hurry to reveal itself. And that quiet is what makes Titan unsettling. A sea without waves forces you to rethink what activity looks like. It reminds you that motion doesn't need to be loud to be real. That change doesn't have to announce itself to matter. Titan doesn't roar. It murmurs. Its lakes don't crash against their shores. They wait. And in that waiting, Titan shows us another way a world can behave. Active, evolving, and deeply strange, without ever raising its voice. But some moons don't hide their oceans beneath ice or clouds. They release them into space. Enceladus is small. Its diameter is only about 504 kilometers, small enough that, at first glance, it shouldn't be capable of much at all. No thick atmosphere, no massive gravity, no obvious reason to hold onto internal heat for billions of years. And yet, Enceladus does something no other moon does quite the same way. It reaches out. Enceladus orbits Saturn at a distance of roughly 238,000 kilometers, embedded within the planet's powerful gravitational field. Like many moons in this system, it experiences tidal forces, stretching and relaxing as it moves along its orbit. But on Enceladus, that energy doesn't disappear quietly inside the ice. It escapes. At the moon's south pole, the surface is cut by a set of long, parallel fractures known as the tiger stripes. These cracks run for tens of kilometers and are warmer than the surrounding terrain. Not by much, but enough. From these fractures, material is continuously vented into space. Not dust, not gas alone, but water. Jets of icy particles and vapor erupt from the South Pole, shooting hundreds of kilometers above the surface. These plumes are not rare events. They are persistent. Variable, yes, but always there. Breathing in and out as Enceladus flexes under Saturn's gravity, the plumes are powerful enough to do something extraordinary. They supply Saturn's E-ring. The E-ring is a vast, diffuse halo of microscopic ice particles encircling Saturn, stretching from the orbit of Mimas out past Rhea. For a long time, its source was unclear. But measurements showed that the ring's composition matched what was coming from Enceladus. In other words, Enceladus is actively feeding Saturn a ring, particle by particle, with material from its interior. This alone would make it remarkable. But the real story began when Cassini flew through the plumes. Not once, not by accident, but deliberately. Cassini passed directly through the jets multiple times, sampling the material as it rushed past at thousands of kilometers per hour. And what it found transformed Enceladus from a curiosity into one of the most important worlds we've ever studied. The plumes contained water vapor. They contained ice grains. They contained salts, evidence that the water had been in contact with rock. They contained simple and complex organic molecules. Later analyses revealed something even more striking: molecular hydrogen. On Earth, molecular hydrogen in ocean environments is often associated with chemical reactions between water and hot rock, particularly hydrothermal activity. These reactions create energy-rich environments that microbes can exploit, even in total darkness. The implication was difficult to ignore. Beneath Enceladus's ice shell lies a salty, global ocean. That ocean likely touches a rocky core, and chemical reactions at that interface may be producing energy. Liquid water, energy, chemistry. These are the core ingredients life needs. And Enceladus wasn't hiding them behind kilometers of ice the way Europa does. It was delivering samples directly into space. This is the moment where Enceladus changes the rules. On most ocean worlds, studying the water means drilling, an almost unimaginable engineering challenge. Kilometers of ice, extreme cold, radiation, time, cost. On Enceladus, the moon does the drilling for us. The ocean comes out. That doesn't mean life has been found. It doesn't mean it's even there. But it does mean the question is no longer abstract. It's testable. The samples exist. They've already been touched, measured, and analyzed, and the data keep pointing in the same direction. Enceladus is chemically active today. The heat that powers this activity comes from tidal interactions with Saturn, sustained by Enceladus's slightly elliptical orbit and its gravitational relationship with neighboring moons. That energy keeps parts of the ocean from freezing solid and maintains the conditions needed for ongoing reactions. Enceladus is not a relic. It is operating right now, and that makes Cassini's story all the more poignant. After more than a decade exploring Saturn and its moons, Cassini was deliberately sent into Saturn's atmosphere in 2017, ending its mission in a controlled plunge. This wasn't just a technical decision. It was an ethical one, to prevent any chance of contaminating moons like Enceladus with Earth microbes. By the time Cassini was lost, Enceladus had already reshaped planetary science. It showed us that small worlds can be powerful, that oceans don't need to be buried to matter, that the search for life doesn't always require speculation. Sometimes it requires sampling. Today, Enceladus stands as one of the highest priority targets for future missions, not because it guarantees discovery, but because it offers access, a chance to study an alien ocean without breaking through ice, without guessing blindly. In a solar system full of distant, sealed environments, Enceladus does something quietly radical. It opens itself, and after worlds of ice, radiation, methane rain, and volcanic fury, that openness feels almost intimate. We didn't have to imagine what lies beneath Enceladus. We didn't have to infer it from shadows or magnetic hints. The ocean reached out to us. And after all that science, sometimes the strangest moments are the ones you can almost feel. After oceans that reach into space, Miranda feels like a shock to the body. Miranda is a small moon orbiting Uranus with a diameter of only about 472 kilometers. At first glance, it doesn't look impressive. No thick atmosphere, no oceans, no dramatic plumes, just a cold, distant object circling a planet tipped on its side. Then you look closer. Miranda's surface looks like it was broken apart and stitched back together. Smooth regions sit beside jagged terrain. Cliff faces rise next to relatively flat plains. It doesn't resemble a world shaped by slow, consistent processes. It looks assembled, as if different pieces were forced into place. The most extreme feature is impossible to ignore. Verona Rupes. This is a cliff that rises roughly 20 kilometers from top to bottom, the tallest known cliff in the solar system. For comparison, Mount Everest rises about 8.8 kilometers above sea level. Verona Rupes is more than twice that height. But height alone doesn't tell the story. Miranda's gravity is incredibly weak, only about 1% of Earth's gravity. And Miranda has no atmosphere, no air, no wind, no resistance. Now imagine standing at the edge. If you stepped forward, you wouldn't tumble. You wouldn't scream past the rock face. You would simply fall, slowly. With so little gravity pulling you down, the descent would take an astonishing amount of time. From the top of Verona Rupes to the bottom, the fall would last around 12 minutes. No air rushing past you, no pressure on your body, just a long, silent drop through open space. It's not dramatic in the Hollywood sense. It's worse. There's no sense of speed to distract you, no noise, no sudden impact, at least not until the very end. Just time. Time to notice how small Miranda is. Time to feel how lightly gravity holds you, Time to realize that physics here behaves nothing like it does on Earth. This is what makes Miranda unsettling. Not violence, not chaos, but scale. And the mystery doesn't stop at the cliff. No one knows exactly how Miranda formed terrain like this. One idea suggests it was once shattered by a massive impact, then reassembled under its own gravity. Another proposes episodes of internal heating that reshaped parts of the surface while leaving others untouched. The evidence isn't conclusive. The pieces don't fit neatly. Miranda doesn't tell a clean story. It feels like a world that barely survived its own history and carries the scars openly. After hours of thinking about chemistry, oceans, and distant possibilities for life, Miranda brings the experience back into the body. It reminds you that space isn't just something to understand. It's something to feel. Through vertigo, through silence, through the strange calm of falling without air. Miranda may not host oceans or chemistry worth sampling, but it leaves a stronger impression than many worlds that do. Because once you imagine that fall, you don't forget it. And some moons aren't just strange because of how they behave, but because they don't belong where they are. By the time we reach Triton, it feels like we've left the familiar solar system behind. Neptune sits far from the sun, where sunlight is faint and the temperature of space feels permanent. And orbiting Neptune is Triton, its largest moon, about 2,710 kilometers across, big enough to be a world in its own right, cold enough to seem, at first glance, like it should be silent. But Triton isn't silent. The first clue is its orbit. Triton moves around Neptune in the wrong direction. Almost every large moon in the solar system orbits the same way its planet rotates, a signature of formation. Moons form in disks of gas and debris around young planets, and those disks spin in a consistent direction. That's why the major moons of Jupiter and Saturn all travel in prograde orbits, like orderly passengers moving with the flow of traffic. Triton does not. It orbits Neptune in a retrograde path, opposite Neptune's rotation. And that one fact changes everything. A large retrograde moon is extremely difficult to explain as something that formed peacefully beside its planet. The simplest conclusion is also the most unsettling. Triton was captured. Not built there. Not born there. Taken. The most likely place it came from is the Kuiper Belt, the cold reservoir of icy bodies beyond Neptune, where Pluto and many similar objects reside. In composition and temperature, Triton fits that family. It's the kind of world you'd expect to find out there, rich in frozen volatiles, shaped by deep cold and made from materials that behave differently at the edge of sunlight. Capture, however, is not gentle. For Neptune to steal Triton from the Kuiper Belt, Triton would have needed to lose a great deal of energy. One of the leading ideas is that Triton may have once been part of a binary system, two objects orbiting each other. And during a close encounter with Neptune, one body was ejected while Triton was trapped. Its gravitational violence turned into orbit. And once captured, Triton would not have settled quietly. A captured orbit is often highly elongated at first. Over time, tidal forces can circularize it, but not without heating the interior. That means Triton's wrong-way orbit may have warmed it long after it should have gone dormant, reshaping its surface and keeping it active in ways that seem surprising for such a distant moon. When we talk about Triton's surface, we're talking about a world made from the kinds of ices that don't play a big role closer to the sun. Triton's surface includes nitrogen ice, along with methane and other frozen volatiles. At Neptune's distance, nitrogen doesn't behave like a trace gas. It freezes into bright plains and reflective layers. It can migrate seasonally, It can form caps. It can move, and Triton has an atmosphere. Thin, but real. It's mostly nitrogen, with traces of methane. The pressure is extremely low, but it changes with the seasons as sunlight shifts and surface ices warm and cool. Triton's weather isn't wind and water. It's a slow exchange between solid ice and gas, a breathing cycle driven by sunlight so weak that it feels almost impossible. But it happens. Then Voyager 2 arrived. In 1989, Voyager 2 flew past Neptune and gave humanity its only close look at Triton so far. The images were startling. Not because Triton looked cratered and ancient, but because it looked shaped, young, active. Voyager saw dark plumes rising from the surface, geyser-like eruptions that climbed several kilometers high before being blown sideways by thin winds, leaving streaks across the surface like ink dragged across snow. These were not volcanic eruptions in the Earth sense. They were eruptions of nitrogen. The mechanism behind them is one of the strangest forms of geology in the solar system. In some regions, Triton appears to have a layer of relatively transparent nitrogen ice. Sunlight passes through that layer and warms darker material beneath it. The heat becomes trapped because the ice acts like a lid. Over time, pressure builds as nitrogen sublimates into gas under the surface. Eventually, the gas finds a weak spot. It breaks through and a plume erupts, carrying fine dark particles upward, which then fall back down and leave long streaks across the landscape. This process is sometimes described as a solid greenhouse effect. Sunlight goes in, heat gets trapped, pressure builds, and a cold world briefly acts alive. That's the quiet shock of Triton. A moon at the edge of the solar system, moving backward through space, still producing activity, still changing, still refusing to be a simple fossil. And Triton's deeper message isn't just about geysers or atmospheres. It's about origin. Triton reminds us that not every moon was born where it is. That the solar system we see today is not the solar system as it began. Worlds migrated, orbits shifted, encounters happened. Some bodies were lost, and others were stolen. When you look at Triton, you're not just looking at a moon of Neptune. You're looking at a piece of the Kuiper Belt that was dragged inward and forced to circle a new master. A displaced world carrying the memory of where it came from and the violence that brought it here. In that sense, Triton doesn't feel like the end of the story. It feels like the revelation behind it. Because by the time you reach this far, the strangest realization isn't just how cold these places are, or how alien their chemistry is. It's how indifferent they remain. They don't need our attention. They don't need our names. They don't need us to be impressed. They keep moving anyway, quietly, consistently, following rules older than curiosity. And after traveling this far, the strangest realization is how little these worlds need us. Tonight, we didn't travel to the biggest planets. We listened to the smaller worlds we usually overlook. A moon slowly spiraling inward, fading toward an ending it can't avoid. A moon so quiet it almost feels empty, and yet still tells a story through what it doesn't do. Ancient surfaces that keep the scars of the early solar system. Hidden oceans sealed under ice, and one ocean that sends its own samples into space. A world with rain and rivers made from the wrong liquid, and a moon at the edge of sunlight, moving the wrong way because it was never meant to be there. None of these places exist for us. They don't need to be discovered to be real. They don't need an audience to be meaningful. The universe keeps moving, quietly, steadily, whether we're watching or not. Thank you for staying with us until this moment. If you're listening at the end of a long day, allow yourself to let go of whatever has been weighing on your mind. Settle into a comfortable place. Breathe slowly. Let your thoughts drift as the universe continues its quiet motion. There's nothing you need to do right now, nothing you need to solve. If you'd like, feel free to share your thoughts with us in the comments. We always enjoy hearing from you. Until next time, rest well and sleep peacefully.